Okay, welcome to lecture number 7. I'm sorry I couldn't be there, but I had to take a trip. So the best way to watch this recording is to actually watch it and put down the Facebook, put down your phone, pay attention like you would in a normal lecture. And there will be some clicker questions during the lecture. However, obviously we don't have the clickers there. So what we'll do is that after this lecture is there will be a short quiz on Moodle. It'll just be the 3 questions, and you should go there and answer them and get that done. The closing time for the Moodle questions will be shortly after when the lecture was done, so please get that done immediately. Okay, so some reminders. Project number 4 is due this Friday at 3:59. This is the SETS project. So hopefully that's going well while I'm not there. So there is this lecture is about algorithm analysis and what we call big O notation. And this actually is one of the things that gives 187 students some of the most trouble. This is an introduction to something more rigorous in computer science. However, it is something that you're going to see time and time again in a lot of your classes, and it's a way to look at an algorithm and decide, okay, how is this algorithm going to scale? So if I give it more and more input, is it going to run in a reasonable amount of time? Is it going to get slower and slower and slower to the point where it becomes infeasible and useless, etc.? And you have to suspend a few things that you already know about computer science. You have to suspend thinking about time as seconds. Okay, you have to start thinking about how does this scale as the size of the input to my problem gets really, really, really big. Okay, so obviously as the size of your input goes to infinity, the amount of time that your program is going to take will also go to infinity. And it's not that we're going to give our programs infinite input, because that's just a ridiculous thing to say. It's that we want to know for larger and larger and larger inputs what is going to happen. Okay, and so we'll see a bunch of examples like this, and we're going to use this when we're talking about all kinds of different data structures. And even going back to linked lists, we can talk about things like how long does it take to find the head of a list and do something there, or how long does it take to find the tail of a list and do something there. And so all of those things are going to come into play. And big O notation becomes really critical for understanding the comparative advantages of one data structure over another. So why is a stack better at certain things than a queue, or why is it useful to have a tail pointer in a linked list, and things like that. So we'll dig into some of that stuff. But this will be a kind of a gentle introduction to big O notation. This is a very deep topic. This is something that if you look at theoretical computer scientists, this is what they spend their whole life researching, is very complicated algorithms or problems and puzzles, where they look at what are the best algorithms, and then are those better than previous algorithms according to their big O notation. So let's start looking at things. Okay, so what is the analysis of an algorithm? So you know what an algorithm at this point is. It's sort of a series of steps used to solve some kind of problem. And this is, an algorithm is really separate from code. A code is source code or a Java program is really an instantiation of an algorithm. It's basically taking an algorithm that has a description and making it into something that a computer can understand. The algorithm is something of a higher order than that. Okay, so what are the resources that algorithms take? And this is what programs take, but what are the resources that they take? So they take time, right? So physical wall clock time, or time on a CPU. On a processor, but they also take space, so memory in your computer, so the RAM in your computer, or if you start looking at things that need even more space than you can find in the memory of your machine. So 32 gigs might be sort of the most memory you can get in a machine these days. And what if you need the disk, right? So what if you need to put some of the data onto the disk and pull that in? So that's all accounted as part of the memory. Most of the things, and in fact, I think all of the things that we're going to look at in terms of the algorithms and the algorithm analysis in 187, we're going to talk about the time. Okay, we're not so worried about the space or what they call memory or space, most of the things we're going to be looking at, or all of the things we're going to look at, is in terms of time. So how long does it take to run this algorithm given some input size? What is the problem size? And a lot of the things that we're going to talk about in 187 are how many pieces of data are stored in my data structure. And that's usually what we'll look at. Other things are possible later, but that's usually the things we'll talk about in 187. Okay, the other thing that we're also going to really focus on in 187 is what is the worst case cost. So what is the worst input that you could give to this problem, okay? And then how long does it take to run the algorithm based on that worst case? A algorithmicist, and when you start getting into the stuff a little deeper, you start talking about things like what's the average case. So if we look at all the possible inputs to this problem, what on average will be the running time? And that can be very different from the worst case. And so you have to think about, what is the worst input that I can give to this problem that would cause the algorithm to run the longest, right? Okay, so like I said, we're focusing on the time complexity of these problems in terms of the worst case running time. So how many instructions or how many steps does it take to run this algorithm? Okay. So let's look at an algorithm and start to kind of analyze, what does this look like in terms of the input size and what is the running size? Okay, so running time. So looking at this, right, we have an algorithm. This is a very simple algorithm. All we're doing is summing up a bunch of numbers in an array, right? So we start with, this happen to be floating point numbers, it could be integers. It actually doesn't affect the problem, and that is something that you will learn, okay? We have a sum that starts at 0. The array has a length, okay, that we'll take. This is not the most beautiful piece of code, but this demonstrates what we're after here. Okay, and we're going to loop through this array n times. So n is the length of the array. So you can see standard for loop. We'll add up all the numbers and then we'll return it. So this is just summing up all the elements in our array and coming up with a number. Right. Okay, so at the beginning we have two assignment operations, right? So we're taking sum and setting its value to 0. We're taking n and assigning its value to the length of the array. And then we go through our loop here. And this is where a lot of algorithms, you start to find what is the running time. What you will focus on in most cases are the loops that you find in the algorithm, because that's where the loops will run longer and longer for a bigger and bigger input size, right? So the input size to this problem is an array. So it's an array that has n elements. And we'll often use the letter n, okay? But it could be x. It doesn't. The n is just a variable, okay? But what we often talk about is the input size as being some number n. So n is a variable and it doesn't have a specified size, right? So what we're concerned about is what happens as n gets big or gets bigger, right? So you can see this loop will run exactly n times, right? N times for an input size of n, right? And okay, so that also returns something. But the critical thing to see here is that if you look at the assignment operations at the beginning and the return value at the end, those do not depend on the size of the input n. Okay, so if you made n twice as big, there's still only 2 assignment operations at the beginning and 1 return value. Okay, and so those things become kind of noise. I mean, they're not really important. If n were infinity, right, this loop takes a long time to run, right? And then these 2 assignment things at the beginning and the return value at the end don't matter, right? Because they're very small compared to the amount of time that it takes to run this loop, right? Okay, so the number of instructions or steps in running this algorithm is actually n plus 3. I mean, you can think about it as n plus 3. Okay, so n times around in the loop, right? And 3 operations that surround it, right? So 2 assignments and a return value, okay? We call this linear. So this is linear with respect to the problem size n. So the thing to think about here is if the array had 3 times as many elements, right? So if n is 3n, right, so if it's 3 times as big, the algorithm is going to take about 3 times as long to run. So the computation grows linearly with respect to n. So as n gets big, right, as it gets bigger and bigger and bigger, it grows linearly. And that 3, so as n gets really big, and you know this from various math classes, right? As n gets very, very big, that 3 doesn't matter at all, right? As n is sort of goes to infinity. And so as n goes to infinity, right? So the 3 doesn't matter at all. So these, what they call, so it's a linear problem. And this is what we will call, sorry, stepping back, this is what we'll call order n. We'll get to that in a sec. So we'll call this order n, which is linear. All right, now, this is a slightly different algorithm. So again, we are adding up elements in an array, but here we're going to, the thing to see here is, oops, sorry, going back, is this statement right here is, I plus equals 2, right? So that is skipping every other element in our algorithm, right? So we're only going to be adding up 0 and 2 and element 4 and element 6. So all of the even indexed elements in our array. So you might say to yourself, well, this will run faster. And you'd be right. This will run faster, right? So if you put this in and you make an array of a billion elements or whatever, this will run faster. In fact, it probably will run in about half the time on your computer as the previous algorithm that added up every element, right? Okay, so maybe it runs about half the time. You'd have to test it. But this is where you have to remember to start thinking like a theoretical computer scientist and no longer think like a real software engineer or an engineer at all, right? So what matters here is that what happens to this algorithm as n gets really big, okay? So how many steps are involved? Well, now it's different, right? Because our loop only runs n over 2 times, right? So it runs half as many times. So n over 2 plus 3, right? Because going back, right, we have our assignment operations at the beginning 2 and the sum at the end, returning that's 3. But this loop only runs half as many times, right? So it's n over 2 plus 3. Okay. So now the thing is that this algorithm, in the eyes of an algorithmicist, right, in a theoretical computer scientist, this algorithm is the same. It's not really the same, but it has the same complexity. And that's the thing to remember, is that this problem also grows linearly with the problem size n. We're not trying to compute how long does this algorithm take to run for a given input size, because that would give you some number like 10 seconds or 1 minute or 5 hours. That's not what we're trying to figure out. We're not trying to figure out an absolute amount of time, because that would depend on a lot of things. I mean, that would depend on the computer that you bought, right? So do you have a fast computer or a slow computer? Are you doing this on a watch or a high-powered server, etc.? So you don't really know how long an algorithm takes to run just by looking at it. You might be able to guess, based on the speed of your computer and the number of operations, but really, when you look at an algorithm, you don't know how long it's going to run. You may have to go out and test it. What we're worried about is how it scales. So how much slower does it get as the input size gets bigger? So this algorithm, as n gets bigger, if it's twice as big, think to yourself, if n is twice as big, how much longer does it take to run than it was when n was half as big, right? So how much longer does it take to run as n gets bigger? And the answer here is that this is also linear. This algorithm is the same as the previous algorithm in terms of its worst case complexity. It scales the same as the first algorithm, because in both cases, as n gets twice as big, okay, the running time will roughly double. So it's not that we're trying to come up with an absolute value. And in fact, when you look at these two algorithms, you say, okay, well, the second one will run faster. And I'm not disputing that. It's that they both scale the same, right? So if you ran the first algorithm on a slow computer and you ran the second algorithm on a fast computer, the second one would actually run faster, right? So if the machine was at least twice as fast as the slow machine, right, it would run even faster. So we're not, remember, nothing to do with absolute measures of time like seconds or hours, et cetera, or even number of operations, in fact. So what we're looking at is how does it scale? And this second algorithm that only computes the every other element in the array scales the same way as the first one. They are both linear algorithms. They're both order n. Okay, so here's the first question. This one is going to be on Moodle. I'm not even going to tell you the answer right now, right? So you look at this, and maybe I'll explain it real quick. But which of these loops takes constant time regardless of the value of n? So this is a different thing, right? So constant time, okay, means that no matter the size of n, so as n gets bigger, the algorithm takes the same amount of time. So in the previous case, as n got bigger for both of those algorithms, both the summing of the array and the even summing of the array, in both cases they got slower, right? They took longer to run as n got bigger, and they got slower in a linear fashion, okay? But there are algorithms where things take a constant amount of time so that they are not affected by the size of n. And you have to look at these all very carefully and figure out which one runs the same amount of time no matter what n is. So you can pause and think about this, and then you can go look on Moodle later and see the quiz and fill it out there. Okay. So there's no answer on the next slide. You have to go to Moodle and try and sort it out for yourself. Okay. Okay. So here's so that's an example of two kinds of complexity. So constant time and then linear, right? So now we have a double loop, and we're going to look at this. Okay, so now we've seen a single loop, which in the previous two algorithms led to linear time. So let's look at a double loop. Okay, so two nested loops, and you've seen things like this. So we'll start with our same array and try and sum something up, right? And we're going to sum up all the squares of all of the elements. So you can see, okay, we have the sum, starts at 0. We take the length of the array. We have two loops with I and j, and these are two very simple loops, right? They go all the way up to n. And then on the inside, we're going to add up the squares of a of I and a of j, right? And so this is an algorithm that just sums up all of the squares, the pairwise squares of all of the elements in the array. Okay, so you can look at this and say, well, how many sum operations am I going to do on the inside of this loop? So if you look at this, right? So if you look at this inner loop here, let's just start with that, right? So this for j equals 0, j is less than n, j plus plus. So if you have a value n, if n is, say, 10, right? So you can think about it in terms of concrete numbers and then make them bigger. So if n is 10, this inner loop runs 10 times, but it runs 10 times for every time this loop runs. So this loop here, so if n is 10, so the length of our array is 10, this outer loop runs, let me just run back one. So if n is 10, right, this outer loop will run 10 times. And for each time this one runs 10 times. So you can start to see, okay, now what if, so if n is 10, this one runs 10 times for every time this one runs, and this one runs 10 times. So what you have is that the number of sum operations that occurs is 100, right? So 10 times 10 is going to give us 100. So it's really the square of n is the number of times that this inner sum will run. And you can think about it just, just to check yourself, right? To say, okay, well, what if n were 100, right? So the outer loop will run 100 times. And for every time it runs, this inner loop runs exactly 100 times. So the number of sum operations here will be 100 times 100, or 100 squared, right? So 10,000. So so now you start to see that this algorithm is very different from the previous algorithm. As n got bigger in the two previous algorithms, right, it was linear, right? So double the size of the input takes twice as long to run. Here, double the size of the input, and what happens, right? It's going to take 4 times as long to run, which is interesting, right? So that's not great, in fact, right? So if you think about it, as n gets really big, this algorithm is going to get really, really slow, okay? So, and it may be okay if the inner loop, if n is relatively modest, right? So 10,000 times, summing things 10,000 times, not a big deal for a computer, right? But if you think that n might get really big, like 1 billion, right? So now you've got 1 billion squared operations that you have to do. And so you might start to think about, okay, I don't know what this algorithm is for, but you might start to think about, is there a better way to solve the problem that I'm trying to solve? Right? So can I get rid of this inner loop for some reason? Can I pre-compute something or do something a little different? Right? Don't know. You'd have to know more about the problem to understand if you could get rid of it. But here, this is running in n squared time. So as n gets bigger, right? So we can step through this, right? So you have n times n operations plus 3, which is the sort of operations on the outside and at the end, right, that we've talked about. So it's n squared plus 3. So it's no longer linear. It's worse than linear, in fact. So we know that as n squared, if you had to pick between two algorithms, perhaps, okay, and if you thought n was going to get really big, right, the order n algorithm will probably, it depends on what n is and the length of time that each operation takes, but what will happen is that as n goes to infinity, the n squared algorithm will take longer than the order n. It doesn't mean that for all values of n, the n squared algorithm is slower. That's a thing that we'll chew on that a little bit as we go. Not for all values of n will the n squared algorithm be slower. But in this case, you probably actually know that. You can actually look at these two things and say, okay, well, the n squared algorithm is going to be slower pretty much for any value of n. That's not always true, and we'll talk about this. So this is what we call a quadratic increase. So it grows faster than linear, so more rapidly. So this is quadratic, right? So squares are quadratic. It's, I don't know, but square, you think about square and quad is a square. That's one way to kind of remember that, right? So this double loop is quadratic. So order, what we will call order n squared, as opposed to being order n, okay? So I keep saying this, order this, or big O this, okay? This is what is known as big O notation. And this is just a notation that algorithmicists and computer scientists use to denote or notate the complexity of an algorithm. And this cost, when they talk about big O, it may be the cost in space. It could be the cost in time. We're really just talking about cost in time. We didn't talk anything about the how much space those algorithms took. We're just talking about time. And so, what is how does it increase relative to the problem size, right? Okay. So O, big O, stands for order, as in an order of magnitude, okay? As n gets sufficiently large, tending towards infinity, we will only care about the fastest growing term. So we only care about the thing that is the slowest element of the algorithm per se. Okay, so you'll see. So what is the dominant term of this? Because what you see is that as n gets big, only this dominant term matters. All right, so we will see that. Constant scaling factors do not matter because it doesn't affect the rate of growth. So if you go back to the previous, the first algorithm, right? So the first loop, right? We didn't talk about how long it took to do the sum on the inside of that loop, right? We didn't say how long does it take to do sum plus equals a of I, because we don't care about that when we're looking at how it scales. So say that took 10 seconds. What would that mean in terms of scaling? Doesn't mean anything, because as n gets twice as big, the algorithm takes twice as long to run, no matter how long it takes to do the inside of that loop. So those constant scaling factors don't matter. Because you can think about it, if you put this algorithm on a faster machine, it will run faster. Maybe it runs half as fast, but that doesn't affect how it scales. If you put that algorithm on that machine and you give it twice as large an input, it still takes twice as long to run. So forget about the constant scaling factors. That's the thing that takes a little bit of time to kind of absorb, right? So you just need to think about the number of instructions, and don't worry about what the cost of these different operations are, because we're not trying to come up with an absolute number. We're just trying to figure out how it scales. So if I double the size of the input, what happens? Okay. So for example, in the first loop, right, we had n operations plus 3 extra operations to do, to take the size of the array and do the return. So that is n plus 3. And as you can see, as n gets really big, so say n was a bazillion, that's not a real number, but a bazillion, that 3 doesn't matter at all, right? It scales linearly. And so this is what we call order n. We just can throw away this plus 3, because no matter what you say about 3 being some fraction of n, so if n is 100, it's 3%, and that's fairly significant. I'll just say, we'll make n a bazillion, and then the 3 gets infinitesimally small as n gets really big, right? So that's what we call order n. Great, that one's fairly straightforward. The next one, n over 2 plus 3, is also order n. And you know that from the first part of the lecture, right, where we talked about as n gets bigger, as n gets twice as big, right, the algorithm takes twice as long to run. That's still true. So we throw away the 3 because you can see n over 2 plus 3, right? The 3 doesn't matter as n gets really big. So a bazillion, a half a bazillion plus 3 is still pretty much a half a bazillion, right? It's very, very close to being that. So the 3 doesn't matter at all. So how can we get rid of the half? Well, remember, it's how it scales. So say if I said the machine was twice as fast, right? Then it would take kind of n to run it. So the constant factors don't matter. You just get rid of them, right? So you just know as this algorithm takes input sizes that are twice as big, it takes twice as long to run, right? It doesn't, these constant factors don't matter. And the same thing is true about the n squared plus 3. So the 3 really doesn't matter as n gets bigger. And in fact, it matters less, sort of less faster than order n, right? Because n squared grows really fast compared to order n, right? So if n is 100, n squared is 10,000, right? So n squared grows really fast compared to n, right? So if you look at some algorithm, right? So say it runs on some problem size n, some n element array, right? And say you figure out, okay, I did this pencil math and figure it all out. It takes 2n squared plus 4n plus 3 instructions to do this. The fastest growing term is the 2n squared, and you know that you can ignore these constant term 2, so the time complexity of that entire algorithm is order n squared. So as n gets really big, the only thing that matters is this first term, and the 2 doesn't matter because you can get rid of these constant factors. So this is kind of takes a little while to start throwing things away out of an equation, but you just get rid of them because they don't matter in terms of how it scales. Okay, So this is just sort of another way to look at this, right? If we graphed, so say you had an algorithm that was n squared, but the inner part of its loop, right, was really, really, really fast, right? And then you had another one which is linear. So say it has only one loop and it goes n times, but the inside part of that loop was really, really, really slow, okay? What you can see that is that for some values of n, as n goes really, really, really big, no matter what these constant factors are, so say it's 0.0001 n squared, all right? So it's some really, really fast operation, but it's n squared. And the other one is really slow but linear. What you see is that this n squared algorithm will eventually be slower as n gets big than the order n1. This is what we care about, is n gets really big, how do these things compare to each other, right? And you can say, actually, so we actually know, we can figure this out. At n equals 10 to the 8th, these things are actually equivalent. As n gets even bigger than 10 to the 8th, this n squared thing gets much slower than the linear one. So no matter what your constant factors are, if you have an n squared, a quadratic algorithm, it is eventually going to be slower than your linear one for some value of n. Now, it could be that the value of n in your program, so this is, we'll step back to software engineering and forget about algorithms analysis. It could be that if you know that the value of n is something reasonable, like 100, right? This first algorithm may very well be much faster, even though it's an order n squared algorithm. So you can't just throw out all of your knowledge of things being faster or slower. At some point, you do have to be an engineer and think about it. But this is, we think about building our systems so that they are robust to very, very large inputs and to make sure that they still work. In fact, you can prove, okay, that as the comparison, so if you look at the ratio of the speeds of these algorithms, right? So you take this linear algorithm, 10,000 n, and you divide it by 0.001 n squared, right? You can see that you take the limit of this, and you can do the math here real quick, you can see that 10 to the 8th over n, as n goes to infinity, will tend to 0, right? And so you know that as n gets very big, as it tends towards infinity, this n squared algorithm will be much slower than your linear one. So you can see any quadratic with any positive leading coefficient, right? I wish things could take negative time. They can't, right? So they're all always positive, right? So eventually it will beat linear. And so this linear term in the quadratic function just doesn't matter, right? And so you get to throw them away when you're talking about the complexity of algorithms. Okay. All right, so this is, again, this is just, we're reinforcing the point here, right? So if you look at on the axis over here, on the y-axis, right, we have different input sizes for a problem, 1, 10, 100, 1,000, right? And we have, we're just going to compare what these terms look like as n gets bigger, right? So what does n to the 4th look like? What does 100n squared? What does 500 look like? So this is some algorithm, doesn't matter what it is, that has these 3 components to it, n to the 4th power, 100n squared, and 500. As n gets big, what does it look like? Well, okay. Right, when n is small, right, fine, n to the 4th is small compared to this constant factor 500. Yeah, okay, so the constant factor kind of is dominating your algorithm at a very small value of n, but we don't care what happens at small values of n, okay? We care about what happens at really big values of n, right? So look, as just n equals 1,000, which actually in many programs actually would be considered as kind of a small input size, right? So at 1,000, n to the 4th is this very, very large number, right? So 1,000, million, billion, trillion, right? So 1 trillion operations that you're going to have to do as part of this n to the 4th part of your algorithm, as opposed to this 500. This 500 seems, quite small now, right? And you can just forget about it, right? It doesn't really matter. So as n gets bigger and bigger, this n to the 4th term dominates. In fact, in this particular case, right, n to the 4th dominates really fast, right? So 1,000 things in your array, not very many, right? You think about how Google operates and Yahoo and whatever else, right? The number of inputs or the number of customers that they have is way beyond that. And so if you built an algorithm, so if you worked at Google or you worked at Facebook or whatever, and you built some algorithm and you go to your boss and you say, I have this new algorithm for solving this problem, but the only minor problem is this n to the fourth part of the algorithm. And they would then laugh at you because you're doing it wrong, right? Because you're going to find out that as n gets big, right? So say n is 1 billion, which is about, I don't know, probably about how many customers Facebook has. N to the fourth becomes some disgustingly large number that even if the inner part of this algorithm that runs n to the fourth times is really fast, the whole thing will be so ridiculously slow that it will never work, right? So this is why you probably won't build algorithms that run in n to the fourth time. And in fact, what you'll find is that even n squared algorithms are considered to be bad because even for modest values of n, 1,000, 10,000, 100,000, right? That number gets really big, really, really, really fast. So if you tried to run some n squared algorithm on all of Facebook's customers, you would bring your machine to its knees, right? It's just infeasible. So you can't think about running n squared algorithms on an input size that's that big, right? So when you're looking at your code now, you start to become very suspicious of any place where you have nested loops, which is often what will lead to something like an n squared algorithm, right? Okay, so just as a summary, right? So look at your algorithm and write down the cost function. You're going to be really focusing on the loops. I mean, this is really where all of this comes out, especially at the beginning with the kind of algorithms that we're going to be looking at, is we're looking at loops mostly. You want to find the highest order term, ignore all the scaling factors, and now you have big O notation. So you're well on your way. Now, it's never this easy, right? So it will actually get much more complicated than this. But most of the data structures that we look at in this class are pretty easily analyzed in terms of their big O notation. We're going to stretch you a little bit, especially in this lecture, because what you'll find is that when you get into later classes in computer science, this becomes a big part of looking at an algorithm and analyzing it. It becomes a big part of those classes, and so this is your introduction to it. Okay. Right. So okay. So now we have a very similar nested loop, but it is subtly different, okay? So look at this, and the thing to recognize, okay, this is very similar to the previous examples that we're looking at. Yes, again, a nested double loop here, okay? But the thing to see here is this thing in red, okay? So our inner loop is not starting at 0 anymore as it did before. Now it starts at I, right? So now it starts at I. So as I gets bigger, right? So I will loop, right? So say if if n was 10, so if our input size was 10, right? The first time, so this outer loop will run 10 times. If n is 10, this will loop 10 times. But the inner loop no longer runs 10 times for every time of the outer loop. It now runs fewer and fewer times as this I gets bigger. So this is a little trickier to analyze, okay? So when I is 0, this inner loop will run how many times? It will run n times. So let's take 10. So it'll run 10 times if I is 0. Then, so you have a run of 10, right? And then this I will increment by 1, right? From this increment here, right? And then so I is now 1. So how many times does this inner loop run? Well, now it will run 9 times. And if I is equal to 2, this inner loop will run 8 times, and so on and so forth, right? So here, this one is a little bit trickier. So the best thing to do is to start writing down examples, because then you can actually sort of do this backwards, right? You sort of write down examples and then try and figure out what the pattern is about how many times it runs. So sorry. So if you look at this, right, it runs n times the first loop. So we're going to write down, so each one of these terms in this sum here is going to be, so we're going to sum up all of these things and figure out how many total times does this sum operation run on the inside, right? On the inside of our loops, right? So first time when I is equal to 0, the inner loop runs n times. Okay, so then the next time when I is equal to 1, the inner loop runs n minus 1 times, right? Because j is equal to 1 and will run from 1 up to n. So this is going to be n minus 1 times on the inner loop. So we have n terms, right? So one term here. So each one of these terms, right? So n and then n minus 1. Each one of those terms is essentially each loop, each iteration of the outer loop, right? So n times on the inner loop, and then n minus 1, and then n minus 2. And if you add all of these up, you may remember this from one of your math classes, right? The sum of all these numbers, n plus n minus 1 plus n minus 2 plus yada yada plus 2 plus 1, is actually equal to n times n plus 1 over 2. And that's just something that you can prove in your math class. And then you look at this and you say, okay, fine. So now I know that this whole inner sum will run n times n plus 1 over 2 times. In some sense, you can kind of think about it. It's almost approximately this outer loop runs n times, and this inner loop will run an average of about n over 2 times, right? Because at the beginning it runs n times, the last one runs 1 time. You can kind of think about it and you can say, okay, well, the inner loop runs about n over 2 times. It's not exactly that, but pretty close. But anyway, so if you sum up all of these terms, right, you end up with n times n plus 1 over 2. So then you look at this and you say, well, that's n squared plus n over 2. I don't care about my constant factor, which is the dividing by 2, so I'll just throw that away. And n squared plus n, as n gets really big, that linear component, the plus n, doesn't matter anymore, and we can throw that away. And so we end up with order n squared. So this algorithm scales the same way. It has the same complexity as if we were doing j equals 0. So interesting. Will it run faster than the double loop? Yes. But when we look at these things, we're not trying to compare the real running time of these two algorithms. What we're looking at is how does it scale with respect to its input size, right? So as n gets bigger, this will scale order n squared. So the best thing to do is to start writing down these examples, right? So in fact, you can actually use real numbers for n and try and figure it out that way. That's another way to do it. Okay, so here's another question. And this is we're starting to build up some complexity in terms of our complexity analysis, right? So look at this loop. Again, this one will be on Moodle, but look at this and you can see, okay, we start with 0, okay? I equals 1, right? That's a little different, right? I up to n. But here, the thing to note, the funny thing about this problem is this right here. So I times equals 2, meaning that each time we run this loop, I is going to get twice as big as we go. So if you look at the pattern, and you can write it down, you can say, okay, well, if I starts at 1, right? Okay, so I starts at 1, and then I will be on the next iteration of this. There shouldn't be a space there in the count plus plus. But anyway, so I times equals 2. So then I will be equal to 2. Then the next iteration will be equal to 4. And then it will be equal to 8, 16, 32, so on and so forth, right? So I is getting big fairly rapidly. So it tends to approach n fairly rapidly. So what is the cost in terms of big O notation? Well, write down some examples of n's that you know. By the way, hint, pick powers of 2. Might be a good way to start. And then look at that and say, okay, well, how many times does this loop run in terms of n? So if n is equal to 16, how many times does this run? If n is equal to 32, how often does this run? And can I express the number of times this loop will run in terms of that value n? And you can kind of work backwards. So look at it and do that one on Moodle. Okay. So, sorry. All right. So, if we look at loops like that, this is giving away the answer a little bit, but this is what we call logarithmic cost. Okay, and if you look at all of these examples here, they're all a little bit different. Okay, but they all actually have logarithmic cost. So I up to I less than n, I times equals 2. What you'll figure out, okay, is that this runs in order log n times. And log, when we're computer scientists and we say log, we mean log base 2. If you are an engineer, okay, if you're, you know, I don't know, in the engineering department, sometimes log, you mean log base 10. So anytime I say log, I mean log base 2, and pretty much anytime a computer scientist says this, they mean log base 2. If you're in doubt, you could ask, but if I say log, I mean log base 2. Okay. Mathematicians might be a little bit more exact and actually tell you what base of the log we're talking about. All right. So this first loop, if you look at it, it accelerates, right? It runs actually, so it goes from I equal 1, 2, 4, 8, 16, 32, 64. It runs, you know, it gets closer and closer to n more and more rapidly, right? And so this ends up being order log n, and we will look at some algorithms in this class that run in order log n times. And the thing to think about is that log n grows slower, which is a good thing, that as n gets bigger and bigger and bigger, a log n algorithm will run, it scales slower than a linear algorithm. So as n gets bigger, right, because if you think about it, okay, if n is 1024, the log of that is 10. So, and if you double the size of that input, if you make it 2048, right, then your log n algorithm will only run, the loop, if you think about it as a loop, will run 11 times, whereas your linear algorithm is now running 2048 times, right? So it got twice as slow as n got twice as big, whereas in the logarithmic algorithm, as the input got twice as big, it only got 10% bigger, right? It scales log n, so it only got 10% slower. And you'll see for really big numbers, like 4 billion, what is the log base 2 of 4 billion? It's about 32. So if you have an algorithm that's trying to operate on something with an input size of 4 billion, right, it will only have to loop around 32 times, which is a really small number compared to 4 billion. And we'll see some algorithms that are like that. You can look at these other things here, and you know, through some various analysis, you can see that these things are just fancy ways of doing division or multiplication, if you know about bit shifting. And this is dividing by 3. And I don't know if we do that this lecture, but we can rigorously prove that actually this, even though it's dividing by 3 and not by 2, that this is the same complexity. Oh, yeah, so I just reminded myself. So we can actually show this to you, and I'll show this to you here in a sec. So this is base 2, right? So we're basically log base 2. If you look at, this is the algorithm that we had showed before, right? So if we're basically multiplying I by 2 every time, right? This will run in log base 2 of n. That's how many times the loop will run, okay? this one, so these two both basically operate in the same way. This bit shifting, right, well, is basically you're multiplying I by 2 every time of the loop. And if you don't remember about bit shifting and about its equivalence to division and multiplication, you can take a moment and go look that up somewhere. Okay, now here we're doing this in base 3. We're basically dividing by 3 every time. So if it's 18, right, if I starts as, if n is 18, or it'll be I will equal to 18, and then 6, and then 2, and then the next time it divides by 3, it will be 0, right, because of integer division, and that's how many times it will run. So basically, as n gets big, right, it runs in log base 3 of n times. This is the number of times that this loop runs. And you can try different examples. You know, try 54, right, so 54, and then 18, and then yada, 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 right? So you can work through those, and you'll see that this runs in log base 3 of n times, right? And then this next one, if you look at this for a second, it's bit shifting by 2. So 2 bits, it's shifting to the right. And what does that do? Divides by 2, and then divides by 2 again, which is the same thing as dividing by 4. So we take a really large number, like, I don't know, 1024, right? If n was 1024, you divide that by 4, you get 256, right? And then if you divide that by 4, then you're going to get 64, right? And if you divide that by 4, you get 16. And then if you divide that by 4, you get 4. You see, it's going to run in log base 4 of n times, which is interesting, right? So this is base 4. We can actually prove that none of this matters, which is one of the great things about complexity, right, is that the base of the log doesn't matter. We still call that the same complexity because they all are equivalent. And this is the magic, right, of if you go back to, you probably learned this one in high school, right, about how to change bases of logs, right? So just looking at, forget about the orders for a second, but the log base 2 of n, if I want to change this to log base e, right, which we remember is called the natural log, right? Why is it natural? I don't know. Who knows? Anyway, log base 2 of n is the same thing as the log base e, or natural log of n, divided by the natural log of 2, right? Because you get the 2, right, from this base here, and the n from here, and basically use the same logs on the top and the bottom, right? So what we see is that, so log base 2 of n is the same thing as the natural log of n divided by the natural log of 2. Now this is funny because the natural log of 2 is some number, and it's a constant factor, right? So it's some number. It's some fraction of 1. I don't remember what it is, but it doesn't matter what it is. It could be a bazillion, it could be 1, it could be 42, or whatever you want it to be, right? No matter what this ends up being, this natural log of 2, you can throw it away when looking at the complexity. So you can say, okay, the natural log of n. So if I have an algorithm that happens to be order log base anything of n, that is the equivalent as saying it is order log base 2 of n, so log of n. So those two things are equivalent. They, yes, you have to go back and you have to say, okay, remember this loop here, right, will run in less iterations than this first loop, right? So this base 4 example will in fact run faster than this one, but we're not trying to compare these, the running time, the real running time of these two algorithms. We're trying to compare how they scale. And that is again, this is the thing that takes the longest to kind of wrap your brain around, right? So these two algorithms, this last one here and this first one, both scale in order log n time. It doesn't matter what the base is. I said, okay, if I say log n, I mean log base 2. It actually doesn't matter for the reasons that I just proved to you. right? So all of these are the same complexity. Yeah. And that you got to work through the math on that one a little bit to totally understand it. So we have classes of functions. Okay, so we think about as we've talked about constant time, logarithmic time, talked about some examples of polynomial time, so order n squared or order n cubed, right? Or order n, you know, what have you. So order n to the third is order n cubed. So these are, we know, just based on intuition and based on the math that we know, right, is that a logarithm will grow faster than a constant. I mean, that's sure, right? As n gets big, if this thing doesn't change, then order log n will grow faster than the constant, right? And we know that a polynomial such as order n will grow faster than a log. Now, it's not to say that within these polynomials there aren't different things that grow faster or slower than one another. So order n cubed grows faster than order n squared. But we think about all those polynomials as being part of a class of functions. And so you'll talk about polynomial time running algorithms. It's not that there aren't different things that run faster or slower within polynomial, but those are called polynomial. And then we have exponential algorithms, which are some of the slowest algorithms that we'll ever look at. In fact, I don't think we'll look at any. No, we will. Okay, later in the semester, we'll look at one exponential algorithm, mostly just to make fun of it, okay, because it's so slow, right? So exponential would be something that grows in, say, 2 to the n time. So you can think about 2 to the n grows faster than n squared. And you can just plug in some values of n, right, to see that, right? So if let's say n is 2, right? So 2 squared is 4. 2 to the n is also 4. So 2 to the 2 is also 4. Great. Okay, so they're equivalent right around n equals 2. But what if n were 100, right? So n squared, so 100 is 100 squared. Well, that's a hard one to do. But let's start with 10. Ignore the discontinuity in my clothing. But anyway, so n. If n is equal to 10, right, so n squared, so 10 squared is 100, right? But 2 to the n, 2 to the 10th power, right, is 1,024. So you can see very rapidly the exponential is going to outstrip the polynomial. The polynomial very quickly outstrips the log, and the log outstrips the constant pretty much instantly, right? So these different classes, and you'll learn, there's much more to this that you'll learn about later in computer science. There's more to it than this, but this gives you a picture, right, of how these things are ordered, right? So 3 to the n or 2 to the n, right? So 3 to the n grows faster than 2 to the n. That's true. N cubed, right, grows faster than n squared. N log n, so we'll actually look at a lot of n log n algorithms. So n times log n. Now, you don't drop the n in n log n. N is not a constant factor, right? If it was 2 log n, you could drop the 2, but it's not. N log n, so you can construct an n log n algorithm by having an outer loop that runs n times and an inner loop that runs log n times. Anyway, you can do that. So n log n grows faster than n. And, all right, so cube, quadratic, right? Log linear. So we'll see this as an example. We'll see this later in sorting algorithms. So good sorting algorithms, such as merge sort, for instance, run in n log n time. In fact, the fastest comparison sorts will run in n log n time. Linear, order n, that's where we started off this lecture, right? And log n, which is better than n. Sorry, log n is better than n. This is log, such as binary search. We'll see binary search later in the semester. And order 1, which is constant, right? So constant we denote with order 1. It could be order 2, which would also be constant, but nobody writes it that way. They always write it order 1. Okay. All right. So if you want to analyze these things, you got to look at how does doubling n affect the running time. It's not that doubling is the right always. It's just a way of looking at it. You could triple n and get the same answer, or quadruple n and get the same answer. Constant function, right? Doubling n, no change. For a log function, it increases very slightly. Less than n, it increases by, or less than doubling. linear function, doubling it will in fact double the running time. For a quadratic function, it multiplies it by 4. And for exponential, it squares, so much, much worse. Okay, so here's another clicker question. Again, this one will be in Moodle. Something to think about here. So for a sufficiently large value of n, which of these things has the largest value? Now, there's a cheesy way to do this, right? Which is to take each one of these equations and plug n into it. That'll work here for Moodle, but or a good way of checking, but not going to work on an exam. So you should be able to do this without the use of a calculator. In fact, we won't let you use a calculator during an exam. So you just look at n and say, okay, well, as n grows, which one of these things is going to grow the fastest? Is it n plus 100, 10 times n to the 4th, 100 times n to the 4th? I don't know. So which one of these things is going to have the largest value? The largest value may or may not be the same as the complexity actually, sorry, backing up, yes. So sufficiently large n, which of these has the largest value? So that's the same as the one having the greatest complexity. So you can look at all these things, n to the 5th plus log n, so on and so forth. So look at these, think about that. Okay. Okay, and then one more clicker question. This one's not going to, well, I'll probably put it on Moodle just to put it in there so you can put it in, but I'm actually going to go over the answer because this one is actually tricky. It's trickier than maybe you think. Okay, so the outer loop here, you can see, this looks familiar, you've seen this, so 2 loops, right, nested loops, I and j. This one goes from 1 up to n, right, up to n, and just note here, right, it is multiplying I by 2 for every version of the loop. So neglecting the inner part of the loop, just ignoring the inner part of the loop, or the inner loop, right? We can see that the outer loop is going to run log n times, and you know this from previous parts of the lecture. You know that that's going to run log n times. But the inner part of the loop is a little bit different. It's kind of similar to another one that we saw, but it ends up being quite different in the end. We're going to start with I, and we're going to count down. We're going to count down. J will be minus minus down to 0, and we're going to add something to this version count. So we'll find out. Basically, the number of this value count here is actually going to tell us kind of how often this loop runs, how many times this inner part of the loop runs. So we can look at this and try and figure out what is the complexity of this algorithm. You should probably take a minute. I can sit here and stare at you. It's kind of creepy, but write down some examples of different values of n. 1 is probably not that interesting, but put in 2, put in 4, 8, 16, and try and figure out how many times it runs for that value of n, and then see if you can figure out a pattern. So I'm going to wait. I guess I could insert some silence here later for 3 minutes and give that some thought and see if you can figure it out yourself. This is the kind of thing that you will need to do during an exam, so it's a little bit tricky. So let's look at the answer. All right, this turns out to be order n, which is crazy, right? Because you look at this and say, well, how is this order n? Well, let's look at some examples, okay? So when n is equal to 16, okay, the outer loop is going to run in the following fashion. It's going to run 1, and then 2, and then I will be 4, 8, and then 16. So the outer loop actually runs 1, 2, 3, 4, 5 times. But the inner loop runs according to what I is. And the inner loop will run according to, it will run 1 time for I is equal to 1, 2 times, 4 times, 8 times, and 16 times. So for n equal to 16, the total number of times that count plus plus runs is 31. If we double n to be 32, the outer loop only runs one more time. It only runs one more time because this is basically log, right? So it's only going to run 6 times instead of 5 times. Okay, but the inner loop runs 32 times because when n is equal to 32, right, the last value of this that is valid, right, is when I is equal to 32, and then this inner loop will run 32 times. And if you add up all these numbers together, you'll see it's 63. And it's very straightforward to see, okay, this actually runs in 2n minus 1 iterations, right? So 2n minus 1. So 16 times 2 is 32, minus 1 is 31. So we get exactly the number of iterations for n equals 16. And for n is equal to 32, 2n minus 1 is 63. And so you know that if something is 2n minus 1, throw away the minus 1. That doesn't matter. That's a constant factor, right? And then the constant factor of 2 gets thrown away. So this ends up being order n. And that's a tricky one. But the only a really good way of figuring this out, right, is to do these examples to come up with what the pattern is. You got to come up, you could have done this with 4 or with 8. Maybe it takes a little less time or whatever. But different values to see how many times this runs. Okay, so this is probably an example of one of the trickiest things that we would give you in this semester. Thanks for watching. If you have any questions about this lecture, I think that Piazza is a good place to ask. I also think, so make sure that you go to Moodle and do the clicker questions on Moodle to make sure that kind of paying attention and everything else. So thanks. See you soon.